Gates once said, "The computer was born to solve problems that did not exist before." Good evening to everyone present here. I'm Kalpal Jain from the Department of Industrial Engineering and Management. It is my immense pleasure to welcome the August gathering. I would like to extend my warm welcome to today's speaker, Mr. Harish D. Dixit. A very warm welcome to you, sir. Also, I would like to welcome all the faculty members present here and my fellow students. Did you know the first computer ENIAC weighed more than 27 tons? From the era where computers occupied hundreds of square feet to the current generation computers, which are light and portable, it has been a journey of innovation and imagination. Today, we are here to learn from an expert who will give us insights on the life cycle of a CPU within the infrastructure world while traversing both hardware and software realms. We have with us Mr. Harish Dixit, who grew up at Ranebennur, Karnataka. He moved to Bangalore to pursue PU education at National College, Baswantaguri. Alumnus of BMS College of Engineering, he has a bachelor's degree in electronics and telecommunication engineering. He completed his master's from Carnegie Mellon University, Pittsburgh. Mr. Harish worked on designing CPUs and memory controllers at NXP Semiconductors Research, Bangalore after his bachelor's degree. He has been at Facebook for the last 3 years as a hardware engineer and is responsible for computer system performance and reliability at Facebook infrastructure. Mr. Harish has 18 patents and 3 conference publications. He is also interested in at-scale architecture research. We are indeed honored to have you among us. We welcome you again, sir. Looking forward to an interactive and informative session. I would request Mr. Harish to kindly take over from here. Thank you.
Thank you so much for that wonderful introduction. It's always good to be back, to your university and say hello to everyone studying there. So for me, it's a kind of a nostalgic feeling. I want to thank BMSC for this opportunity. Thank everyone for coordinating this event. I know it's pretty challenging to coordinate things virtually. So today I'll be talking about, as you mentioned, about the life cycle of an infrastructure CPU. And I'm using CPU as sort of a vehicle to show what happens in an infrastructure. What happens when you do a Google search? What happens when you search for something on Facebook? What happens when you call an Uber? Right? So there's a lot of things that go on in the backend, and I want to give people an overview of what happens in the software layer, what happens in the hardware layer. And we'll go through the journey from the hardware realm to the software realm. I call it realms because usually they don't talk to each other, but at some point they intersect. So let me share my screen and we can get started with the presentation. The first thing we'll cover today is why am I talking about CPUs, give an overview of what CPUs are about. The second thing we'll walk through is what does semiconductor industry comprise of, and what does the infrastructure industry comprise of, and how they work together. So there's actually a whole supply chain, which is from the material engineering space, industrial engineering space, to fabrication space, to electrical engineering, electronic engineering, finally to computer science. So everyone needs to work together to ensure that this happens. We'll walk through an example use case. I don't want to talk about theoreticals. We'll use the example as a layer so that you can develop your understanding. We'll walk through the hardware design of that example, just a very generic block diagram sort of stuff. And then we'll walk through the large scale software design example. Let's say we had an application, how would we design it? And then we bring it all together. We'll run a query and then we'll see how we walk through that query and what are the expectations that are set within an infrastructure for that query. And finally, we'll talk about some lifecycle challenges, like what are the biggest problems that we see, and talk about one of the cutting edge research problems that we are working on across the industry. And finally finish with a couple of design philosophies at scale. So the things that you would see when designing a laptop is totally different when you design a data center or a large scale infrastructure. So I want to imbibe a few philosophies, if you want to go and pursue a career in this domain, how would you think about things? Right? So as was mentioned in the introduction, right, the silicon density as well as with respect to the computing industry itself, we've gone from having 29,000 transistors, each transistor is as big as the size of a book, to currently having 1.7 billion transistors, and you can't even see the transistor anymore. It's smaller than the width of the head. We've also gone from having very simple CPUs, which could do standard numeric computations. You would multiply two numbers, it would give you a result. to actually having special function units. What do you mean by special function units? There is a block which is called as AVX, which stands for vector instruction, which does advanced data processing. Think of like 1 million instructions per second across like tens of thousands of CPUs, right? And all of that could be done within a single CPU, like, if you just see the journey. There are floating point units which are used for approximate calculations. There are also like recent trends where people are now realizing machine learning is the biggest application, and CPUs are now taking in the form factor of a machine learning computation and putting them into their hardware design. And finally, we've also gone from having transistor sizes like of 10 micrometer to like 5 nanometer, right? Actually, the graph only starts at 1970, but people have been working on since 1950, and you could actually see with a microscope or like with a magnifying glass, like, okay, what would the transistor look like? So the technology that has technological advance that has happened in the material science and fabrication space has enabled us to get where we see small devices, mobile devices, and all. So let's level set, right? I know there's a very broad audience here. So what does a typical CPU block diagram consist of, right? So you want some job to be done. Like you literally use a computer unit to get some computations done. What you would do is you would say, okay, give me the computations that I want to do. So this is what is basically done by the fetch unit. Fetch unit takes the computations from the memory and says, okay, this is the computation I'm supposed to do. Compute units execute on that computation to say, okay, 2 times 3, I will do 2 times 3. Execution context is basically your bookkeeping, right? When you're multiplying maybe tens of thousands of numbers, you want to bookkeep and say, okay, where should I add this? Where should I take this number from? So it's basically a bookkeeping context that every CPU manages. And finally, there is device management. Like every CPU connects to hundreds of devices, and you would see that, you will need to ensure that device connects correctly. It is able to transfer data. It is able to understand the computations. So that is device management. And if you talk to a hardware engineer about CPU, they would talk about all these things which are on the left side, which is power, performance, like, what is my silicon area? Is it functional enough? Do I have crosstalk? A crosstalk is basically like, 2 wires very close to each other and they start interfering data with each other. There's material science evaluations, there's simulation, there's fabrication. So hardware engineer understands this block in one way, right? Then there's a software engineer. If you speak to the software engineer, they would say, I don't care about any of this material science stuff. I care about application performance. I care about thread efficiency. I care about my kernel, which is like the most secure part of your operating system. I care about my operating system itself. I care about which language do I write the code in. I care about how that language gets translated by the machine. How fast can I execute? So you can see that this one component, based on who you speak to, has different opinions, and the things they care about are very different. So when you design something like this, you're basically taking input from everyone in the industry. And in the middle of all of this, there's a very tiny block which is called as BIOS, which ensures like, both people kind of can talk to each other and gets the machine to boot up. So before we go to the use case, I want to take a step back and look at how the industry functions, right? So there's a plenty of like plethora of business cases, and all these companies have a say in what happens to the next technology event. So the first set of companies that I want to walk through are like the foundries. Right? So these are the folks who are doing physical deposition of your silicon. So like they would take the materials and they would like lay layer by layer, and you will eventually see a chip. So this is like some of the top 3 or 4 companies which kind of do that. And they work with the CPU companies. So typically, like the world currently has like 3 prominent players, Intel, ARM, and AMD. There are open source CPUs in the making, but for now, let's just limit the discussion to these. So these folks would give the design to these foundries, and they would say, this is the CPU I want you to print. So think of these as like, designers, and then the other folks as the printers. And then there are 2 very special purpose like functions which are used in the infrastructure space. One is the BIOS. There's almost a monopoly with respect to this. There's a company called AMI. When you boot up your CPU, or like boot up your machine, if you hit delete or F10 based on which device you're on, you'll actually go to a blue screen. So that blue screen is a software written by a company called AMI for most companies, for most like laptops and such, and they control what goes in that particular software. And then there is also the kernel, which is like the secure part of your device, which you typically don't see when you're using laptops. But when you run a large-scale infrastructure, you would want to control how the secure part of your operating system kind of work. And finally, like let's say we have designed the CPUs, we've printed it, we've prepared the BIOS, we've prepared the kernel. There are two different forks that happen like at this point. One is people design servers and they say, okay, I am a server designer and I will sell this server design to the market. And they are what we call as OEMs. OEM stands for Original Equipment Manufacturer. So these are your Dell, HP, Cisco, and all such. And then there are other folks whose use cases are not satisfied by what Dell, HP are providing every day. They want to innovate on their own because they know their use cases are bigger. And that's where like Google, Microsoft, Amazon, and Facebook come into the picture. So these four companies especially are termed as hyperscalers. And within these four also I've kind of split 3 and 1. The reason 3 and 1 is because Amazon, Google, Microsoft also sell their infrastructure. So for example, today, Netflix runs on Amazon Web Services. So if Amazon goes down, Netflix goes down. So that's how you see a relation. Facebook is the only company today which does not have a cloud infrastructure. So there's a difference in the operating model. There's a difference in the business case on how all these companies connect together. So basically, everyone talks to each other. Everyone has their own business requirement, and they kind of make sure that things work for them. So let's start with a use case, right? Let's say you're part of a large infrastructure company and you want to see one application turn into reality. So let's start with a word processing example. You have a hyperscale application. You have 100 terabytes of text. And it's not even a joke, right? Like we typically see 5 to 10 petabytes of text every day, but 100 terabyte is just an example. And the first thing that happens is you have this text. Like there's a use case here, like there's a business use case here. Like for example, you could do content understanding with the text. You could say, I want to understand how sentences are related to each other, and I want to run machine learning algorithms on that. You could do translation. You could say, I want to translate from one language of text to the other language of text. And you could also do word grouping and enable search application. So you could say, this is my table of words. This is where they are. And I want to identify all the sentences by most relevant search terms. And so this is what is identified by folks who are called as software architects within these hyperscale companies. And I have a question. What exactly is a hyperscale application? So any application that requires large processing is called an at-scale application. So when I say large processing, think of it as at least 1 million CPUs or more. And a hyperscale is an order of magnitude higher than that. So it's just a term to show that the volume of data as well as the volume of computation that we're dealing with is pretty big. And that's the terminology that is associated with this. So the second set of requirements are done by infrastructure designers. So you have this application, like 100 terabytes of text, and you want to process that 100 terabytes of text. We decided our business case, and with respect to software requirements, we now start to looking at how many machines do I need to satisfy this application? How should I distribute? Like I have 100 terabytes, should I distribute them as 10 files, 1,000 files, 10,000 files? I don't know, right? So I need to decide on those numbers. I also need to decide how much power I can consume. So when you run a data center, the most constrained resource that you have is actually power. And it's very difficult for you to find power because it costs a lot. So what people try to do is they want to optimize their applications for power and make sure it consumes as less resources as possible. And finally, you also have to decide like how many regions you want to deploy your application in. So when I talk about regions, it's basically like think of companies like Google, Facebook, or anyone having data centers across the world. So they have a data center in Singapore, they have a data center in Sweden, they have a data center in Denmark, they have a data center in US, they have a data center on southeast of Korea, right? So these data center locations are spread out. Now, as a software designer, I need to understand which region cares about this application more and make sure my software is running on that region efficiently, right? So you need to do a regional allocation. So this is done by a set of people who are called as production architects. And finally, they translate this requirement and they give to the hardware architects within the same, like Google's and Facebook's of the world. Right? So they translate this number of machines, power, number of regions requirement to actually the definition of things within the CPU. So they would say, okay, which unit should I use? Should I use a CPU? Should I use a GPU, which is typically used for like Bitcoin mining or like, machine learning applications? In this example, we're sticking with CPU. You have to then understand, okay, what should my CPU power be? What am I willing to pay for it? What is the performance that I'm supposed to get? So they prepare a specification document, which is basically saying, this is my business case. This is what I want to achieve. These are like the minute details that I care about. And they hand it over to the CPU vendors. So in our previous slide, we saw who those CPU vendors were. Right? So those CPU vendors will take these specifications and they will start working on it. And they go through all of this stuff. I will walk through each one of them in general terms as high level as possible. Again, please feel free to stop me if there are any questions. So the first thing they do is once they get the requirements, they will break it down into different blocks that the design should incorporate. So this is basically design partitioning, right? So you get a set of requirements and you're like, okay, what can I do together? What can I parallelize? What needs to be sequenced? So you need to understand how there is a dependency within a CPU to ensure that you're translating the requirements into like function blocks. So once you decide, okay, this is my block diagram, right? Every block gets assigned to usually a whole team. So one team would work on one block. A team would comprise of like anywhere between 20 to 30 people. And they would then write your typical Verilog code, right? So I'm not sure if people are familiar with it, but you write hardware design using a hardware language, which tells you this is how my gates should be, this is how my transistor should be. So you write that code in Verilog language. I mean, more predominantly Verilog in the US. Actually, a lot of European companies still use VHDL. So once you write your code, you will have a separate set of teams who will then come in and say, I want to check the code that you've written to make sure that the hardware would work. So that is basically done using technologies called as UVM. Do data centers work on CPU nodes only too, or are GPUs always there with CPU nodes? So it's a trade-off decision. We are actually in the middle of, even within Facebook as well as within Google, it's always understanding how many CPUs do I need and how many GPUs do I need. That's actually like a partitioning that is done based on how good your software is. So the key thing that people care about is parallelism, right? So if your code is parallel, which is usually the case when you do images, right? So one image is independent of the second image. So if you have no dependency between your workflow, you could process both of them together. And that's when you would say, let's use GPUs. But if there's a dependency, typically, you would then use CPUs. But at the same time, like this is just from an applicational profile. But at the same time, there's cost and power associated. The cost for GPUs is significantly higher. There's also a significant market demand. You might have read reports of NVIDIA GPUs being in shortage all the time, right? Like people paying 3x, 4x the amount. So when you want to run an infrastructure like which is of hyperscale, you also want to make sure that you have devices available to be bought. And you want to make sure like you're paying the right cost for it. So people will try to use the resources that they already have. And only when the business case or like the application case is justified, they will then switch it over to the GPU section. So we were at verification, right? So someone writes the code and you would want to verify it to say, are you doing the right thing? So I'm listing some terms here so that you're kind of familiar And if you want to Google based on this, right, you can go ahead and say, oh, hey, what is UVM? And you would basically learn what is the, the advanced technology that is used for verification today. The next thing that someone would do is they would take the code, they would put it on devices which are called as emulators. Think of these as devices like similar to the devices that you play on with the labs, right? So I don't know if everyone here has worked with a logic board. You would put in a chip, you would say, what if I turn this on and turn 2 lights on, 1 light off? Does that behavior work? Like, think of this as scaled up. Like, instead of having 2 inputs, 1 output, like you have like 20 million inputs and 20 million outputs, and you would use an emulator board to verify that using like your test cases that the device is working correctly. So the goal here is to just verify electrical properties of the device. So once you have verified, you have validated, what you would do is then you would convert it, right? So currently we are at a block diagram and a language level. What you want to see is actually a physical chip. So now we start the journey of going from like block diagrams towards the chip. So the subsequent step there creates your gate diagrams. So from the block diagram, you now go to gates and you prepare a layout of the gate. So this is what is called as synthesis. And once the gate diagrams are completed, you actually come up with a physical layout of the chip. So this is literally coming up with like some CAD tools and saying, this is how close one transistor should be with respect to the other. This is how far they should be with each other. If they need to talk to each other frequently, you want to put them close together. So this is basically like space management within an X-ray of the chip, right? And finally, you prepare this like CAD diagram. You have all these functional blocks, gates, and everything translated into like these material level blocks. And you would say, go to the foundry and get one of those foundry companies to print your device for you. And the way they do it is very similar to like 3D printing. I mean, I'm simplifying it a lot, but what you do is you do layer by layer, like deposition, and finally say, okay, whatever layers you requested, I have prepared them. The foundry would come back and send the chip back to whoever was the designer. So once you get a chip back, what you do is you run all the tests that you ran before. So whatever test you had prepared for verification, you modify the tests and run them again, because you want to verify that the physical fabrication of the chip has happened in the way that you expected it to. So you're meeting a business case, right? Like, we want this eventually to serve the application that we're designing it for. So you would run automatic tests on the chip and you would bin them. So the binning is a process where you say, this chip is sort of good, this chip is really good, this chip is in the middle. So actually you end up paying different prices for these 3 different bins. And based on how critical and how demanding your performance, you will pay more. All right. So that's basically what the binning process gives you. And finally, you load up the BIOS, which is like the first thing that you would load up on a CPU, and you would validate it so that it runs. Now you would have gone through all the process of the design, and then you would run against your application and you would talk about, okay, this was the application requirement. How much am I able to meet that application requirement? And you compare it. And if it's not, you actually do all of this again. If you have any issues with respect to your functional correctness, what I mean by functional correctness is if you're multiplying 2 numbers and the result is wrong, you would do all of this again. So it's actually a very iterative process. The whole process that I'm describing here usually takes about two years in a typical life cycle. So at the end of all of this, you now have tens of thousands of CPUs, which are ready to be shipped to whoever your customer was who gave you that specification. So we have tens of thousands of CPUs, right? And this is received by companies like Google, Facebook, and all of these. Right? What they do is they put CPUs in a box, which is called a sled. So what is this sled? as you want to scale up, you want to build more and more of these. You want to ensure that the space that you have is managed effectively. You're delivering power to the CPU. You're making sure it works. So you put the CPU together, and you put it with the memory. You put it with your hard disk. You put it with your cables and all of that, and you ensure the form factor is as small as possible. What form factor basically refers to the size and the width of the sled. So once you put the CPUs with the sled, with other materials, you have one server. You put one of these server, multiply them by thousands, and you can finally put them together in a structure which is called as rack. So all of these go through, you construct a rack. Once the rack is ready, you do your testing again, because you tested on the CPU initially, you built your sled, you put them in a rack, but you don't know whether things would work just by connecting everything together. So what you do is you do an integration testing, and this is a process that usually takes 3 months for any typical industry application. And finally, you ship the rack to the data center. So this is actually what gets shipped to every customer. And all of this process is managed by another set of companies, which are called as ODMs. These stand for original design manufacturers. So they take in the specifications from companies like Facebook, Google. They prepare all of this. They build racks, and they say, here's your rack ready for you. Please take it. And this whole process is called as manufacturing. So this is what is called as the manufacturing of a rack. Right. So you've designed a CPU now. You've built a rack out of it. Now the rack is received at your data center. That is when the software design begins. Right? So you had your application. You had 3 segregations that you had done with respect to your application. Then you start making software trade-offs. Right? So you could decide partitioning based on a number of policies. So you could say, I want to sort all of this text alphabetically. I want to break them down into files alphabetically. You could say, I want to break them down into regions where they're coming from. Let's say, a lot of files are coming in from India. Maybe I want to bucket all the data from India into one region. You may also want to choose to partition your data from the date of creation. I care about data which is created in the past 3 months. I care about data which was maybe a year ago. So you could make choices similar to these 3 fields. There could be many other fields, and you could decide, okay, this is how I want to partition the data. There could also be policies that influence how you design your software. Am I caring about the speed of the application? Am I caring about if the application is 100% or it is 95% accurate? How much power do I consume? This is what I mentioned before as well. How many machines do I consume? Or do I only care about accuracy and I don't care how fast I work? So what decision you make here totally decides how your application structure would look like. And this is basically a process that usually takes 2 to 3 months again. So 2 years for silicon design, 3 months for manufacturing, and now we're in software design phase, which is 3 more months. And finally, you have some well-known architectures. Again, I'm putting some terms here which I'm not explaining, especially Spark, MySQL, but these are terms for you to go and search and read up if you're interested. So there are some distributed system architectures which guarantee you consistency, which guarantee you speed, which guarantee you reliability. They will say, if you put the data in this format using this architecture, you will not lose the data. So when decisions like this are made, sometimes you might go ahead and say, look, I just want to use what is available in the market. I don't want to design anything on my own. Or you could say, no, whatever is in the market is not satisfying my use case. I want to do something new. And that is where you would go and say, I want to build my own distributed system architecture. And that decides how all of these policies and partitions are made. Since TDP of a CPU depends on the hardware as well as the software design, does the optimization by the 2 groups happen parallelly or one after the other? That's a very good question, actually. So what happens typically is 4 or 5 racks of whatever hardware design has been completed will be sent well in advance. right? So during this 3-month period, the software team actually has access to 4 or 5 racks, and they would try out different policies and evaluate what performance they get. So they would say, what if I partition by alphabetical behavior and do all of these decisions? How much would I get from this CPU, whatever design is done? So it needs to work in tandem. And like usually it's a set of software architects sitting in the room with a set of hardware architects and taking feedback from hardware architects and then designing this whole flow. So they do have some test tracks to play with, which can give them a bit more insight. And you're absolutely right in saying that they have to go together. So once you've arrived at your software design architecture, what you want to then focus on is software efficiency. So think of this as the same scenario where you were doing hardware, right? You had your block diagram, you created your block diagram. Now you go and optimize your block diagram. For software efficiency, it's the same thing, right? You've decided this is how I want to write my code. Then you start optimizing the code, right? You could optimize with respect to compilers. Like you could write your code and you could say, hey, when you're compiling this code, use this specific instruction only, or use this instruction but keep it alive only for 30 instructions, or use this special library which is like 10x faster, but maybe costs 2x more power. So you have all these choices when you compile your code to flag to the compiler to say, I want this because I really care about this. So these are like some compiler optimizations that you can work. The second set of things that happen are called code and access optimizations. So this is about ensuring you have the right access pattern. So what do I mean by access patterns? Right? You ideally want to access data which is close to each other. Because if you bring in one piece of data, it will usually bring in its neighbors along with it. Right? So you want to ensure that if I get the data, I usually end up accessing the next set of data which is already brought in to my temporary memory. So that's efficient access pattern. The second is efficient variable use. If you do not want to have a code where there are like 10,000 variables and you only use them once. What you would want to do is like reuse variables so that you're kind of efficient with how you're managing the whole code. Avoiding memory leaks. So think of this as a scenario where you keep assigning variables, but you never delete them. You keep saying, I want 10,000 array locations, but you never actually use 10,000, which will end up creating like a memory leak. So what you want to do is like really evaluate how many slots you need, how many variables you need, how quickly and how consecutively can you access, and where possible, parallelize the code. So if you know that one set of work within your software library is not dependent on another, and they can eventually synchronize at some later point, what you want to do is you want to split them up and say, run these two in parallel, finish one first, maybe wait for something else to finish, and then finally say, let's join the results together. So that's done by another set of teams. And the final part here is kernel OS optimizations. This is typically in the Linux kernel. Code patches are submitted by everyone. So this is across the world. There's a whole community which contributes to like ensuring the kernel as well as the OS is optimized. So this could be improvements to your libraries. This could be improvements to your system memory management. This could be improvements to like, ensuring your machine boots faster because you're now able to load pages faster. So there are like a lot of things which go on in the background, which usually people don't see. But if you just go to like GitHub for Linux kernel, you will see like every day there are like 10,000, 5,000 patches where people are trying to say, if you do this, our kernel, our function will become maybe 3x faster, or it is 2x more efficient. And all of that happens for every application within a large-scale company. So let's bring it all together, right? Let's walk through how the word processing would be done, and let's walk through like the query, and then let's walk through like how quickly do we expect the response to be. So we split the 100 terabyte into like indexed partitions. You would split it based on the policies that you've made, and you would then say, this is like, this partition is stored here, this partition is stored here. So you would create like a queryable database. A queryable database is basically something that you can write code for and get the exact data that you're asking. So once you set up queryable databases, you want to set up queries that run every day because you want to keep the data fresh, right? Like let's say I have some data that is stored and no one accesses it, it becomes stale and it stays like in some of these backup copies for like 3 to 4 months. But if I want to especially run a search, I want to keep the data live. So what I do is I typically run queries to get the data to be fresh and to be refreshed. So once I do this, I create an index of the result to say, today this is the index, this is where the column is, and this is where the data lies. I have a question. So there is a rise of fixed functionality processors which provide better performance. What problems can be expected to assign to specific hardware in the future, and are general purpose CPUs dying? So actually a very good question. So the fixed performance devices like TPUs, as well as like a couple of ASICs that Facebook just published about, they're mainly meant for high throughput machine learning inference applications, and they usually serve a specific use case of image processing or inference recommendation. So what do I mean by inference? It's like you've trained a machine learning model, and that model you have now deployed in production, and you're using that model to say, is this a cat? Is this a dog? Right? So you're using that for like million computations every day. And for those applications, the software as well as the workload profile is very well defined. That is what currently within the infrastructure space, these TPUs as well as the inference logic is used for. On the question with respect to general purpose CPUs dying, that is something that we are seeing for sure. We are seeing the end of Moore's law, which is typically every 2 years you see the performance of the CPU double. But now we are seeing that instead of 2 years, it's actually 4 years. And the reason behind that is we are not able to move forward with the technology nodes, and that's what is causing the folks who are in the infrastructure space to say, right, the CPU is not moving as fast as possible. Let's identify the applications within the CPU and partition them so that we can understand the profile and put them on ASICs. So you will definitely see in future a lot more ASICs or TPUs put around a CPU, and you will have these heterogeneous architectures where CPU does what it's good for, and for all these machine learning applications as well as image processing applications, you will see special purpose ASICs spread around it. So a future server may have one CPU, 20 different chips, all for special function use cases around it, and that would probably be like put in a sled, and that sled would get part of a rack. Sorry for the long answer. Hopefully that answers the question. So we index the results and we store the results for future use. So we have now completed a scenario where, as a manager of the data, I have processed my word groups. Right? So this is basically what happens in the backend every now and then with any of these infrastructure companies. So now let's say a user performs a search. Let's say you're sitting in Bangalore and you're trying to perform this search. And you say, I want this keyword and I want all the sentences associated with this keyword. And I'm querying from location A. So you would usually give that out. So what typically happens is when you do this query, it goes to a location which is called as a network cache. And what is a network cache? So think of these as your internet providers. So companies like Airtel, companies like Vodafone, they usually maintain a very small facility, like every, you can say 400 kilometers in India. And they cache some of the most accessed data for that particular region. So when you do a search, the first place it looks up is actually to go and look at these Airtel and wireless provider managed infrastructure. And it says, do I see this data here? And if it is present, the data is sent back immediately. So you have a better response time for your search. If it is not, it goes to the nearest data center. So for example, it could go to Singapore, it could go to Southeast Asia, wherever the closest data center is for whichever query you're running. It will go and check there to see, does this data center have the data that this person is requesting? And the data center also maintains your cache. If it's not there, it will actually end up going to a separate data center, right? So imagine your data is only stored in the US. If there is a cache miss within your local data center, it will go fetch the data from the farthest data center, or wherever your data is. Like it will try to optimize for distance and make it as short as possible. But if it's not, it will eventually go to the farthest data center, if it's not there anywhere, and get you the data. So once the data is available, it finally starts processing the data. Right? So we have done your word groups. You will then go and say identify search term and its index. So basically, whatever word group processing you have done above, you will just start accessing that. You will then bring the partition. So because you want to compute on the data that is there, you will bring the partition to a current processing pipeline. So this makes the data as fresh as possible. Once it is there in the processing pipeline, it will search within the index. If you are searching for a specific string, multiple sets of strings, if you put in any conditional modifiers, anything, it will search within that index. And finally, there's also this relevancy factor. So every time you search, right? So you have an option to say most relevant, new, most popular, and all of that. That means you're basically putting an order request to say, this is how I want the data to be sorted. So that sort also needs to happen in memory. And based on the data that is received, you would then sort the information. And finally, you would execute a data transfer to the region. In this case, it will update your nearest data center to say, hey, one person accessed data from this region. So maybe you should keep a copy of it in case someone else accesses. So that happens within your data center cache. And it also updates the nearest wireless that if someone else accesses, they don't have the same round table time that you needs to happen within 100 milliseconds, more often than not. So all the steps that you saw have to work within that particular time frame. Otherwise, you just see slowness with everyone using that application. And all of this in the backend, for this particular example, it's running together on tens of thousands of CPUs, and all have to work in tandem. All the code that is written, all the CPU design that has been done has to work so that this process works smoothly and you get your search term back within 100 milliseconds. So this is basically the whole life cycle that is associated with the device as well as with respect to the application. So the question is, what are the challenges that you see, right? So you've designed whole of this problem, whole of this domain space. What if the most important block doesn't work? What if you do all of this and when the user performs the query, the identification part for the search term and its index, it never returns. What you end up seeing is the person keeps performing the query and you always say, no, I don't have the data. And this is what we typically, want to avoid as part of people who are managing the application. And as I mentioned, what if there's no residue? You don't know why your search is failing, but at the same time, there is no log, there's no printf, there's no information. Basically, there's no instrumentation at all as to why this is failing. So usually when you develop software, you put an instrumentation and you say, if it fails, show me this. If it fails, maybe print a log into this database, which is called as a debug database. But if there's a fundamental error within the CPU itself, there's no way a software will be able to detect that. It will just say, sorry, I don't have the data, but I don't know why I can't give you the data. And imagine a scenario where you're searching for something and instead of taking 100 milliseconds, it suddenly takes 1 minute for every now and then. And you don't know why that happens. So these are example problems that I'm creating here to show the kind of challenges that usually the teams work through. There are a couple of papers published on this, which talk about especially the last two scenarios that I mentioned and how teams kind of resolve through that scenario. So this is a very interesting industry example, which I'm giving for the exact same problem that I described. You're searching for something and the data is not there. And we published a paper around this and it shows how things like this can happen because of a faulty CPU. So let's consider the application, right? You have put all the data in the files and you now say, please give me the file, right? So one of the application is requesting, this is a real world use case that I'm describing here. One of the application was requesting a file, and when you requested a file, you are saying, okay, give me the file size and give me the data. But the computation unit, which was doing the processing, came back and said, sorry, I don't have the data. So the database said, this file does not exist. Imagine a scenario where you write your data but it goes into a black hole and there's no response from the database. And this was all because one CPU was computing like something that is so fundamental that you expect a CPU to never get it wrong, gets it wrong. So you're computing this computation 1.1 to the power 53. You're expecting a number, right? That's what you expect out of your CPUs. This is the fundamental contract we have with our CPUs. And the result is 0. So what this meant was it kept thinking there was no file. And you end up with missing rows in database. So this went on for 3 months. And we eventually root caused it to the failing instruction, right? So an example error here is, you compute some positive power, it gives you wrong values. You compute some higher power, it gives you incorrect, like, by an order of magnitude. And even if you compute a negative power, it actually gives you the wrong answer. So what problems that we end up are usually like, needle in a haystack problems, right? So there's so much data, there's so many places where it can go wrong. And for the application to fail, all it takes is one corner block, doing one corner mistake, and you're you're at a risk of not meeting what your search term is or what someone is asking you. And I'm putting an increasing risk of failure graph here to show if there's a risk in the application code, you can just immediately rewrite your code and say, fix it, and you can deploy the code within 15 minutes. You could do the same thing with compilers. You could do the same thing with software configs. But the risk keeps exponentially increasing based on where the problem starts. So if there's a problem with the CPU correctness, then you have the problem with the most fundamental block. And you basically have to swap it out. But then you're afraid of how many CPUs have the same problem. Right? You've deployed tens of thousands of CPUs, and you don't know how many CPUs have this problem because the error that it made was data dependent. Like if you ran different computations, you will see correct answers. If you ran only those computations, you will see incorrect answers. And that's an uncertainty as a reliable infrastructure, you cannot afford to have. So there's an increasing risk of failure. On the right, you see like a debugging flow, which starts at the application for the issue that I just described in the previous slide. And you end up going from the application to compilers, to software configs, to OS configs, and finally, debugging through like 500,000 lines of assembly code, and finally saying, okay, this one assembly code, this one instruction fails. And that's not something that you would like to do, right? This is a very painful task. So what you want to do when your infrastructure wants to be reliable is put safeguards and ensure whoever is manufacturing the CPUs is doing a good job, whoever is writing the code is doing a good job. So it basically takes everyone involved in this process to do their part for ensuring that the infrastructure works. So let's say you have a new application, right? You start with 100 billion images. We have to do everything all over again. We can transfer some lessons. We could even decide whether CPUs are the right application for this, right? You could go with GPUs because it's images and there's no dependency. Like every image is independent of each other. With text, there is like some semantic dependency on like one line following the other. But with images, each of them are separate. So you go through the whole exercise that I described, right? Hardware design, vendor selection, software design, software architecture, testing, application deployment, application performance analysis, ensuring reliability, and you say, right, here's your application. So that's basically what happens in the backend when you see someone launching a new feature or when you see Google updating their search. So this is basically how they come up with their solutions. So I want to leave this audience with 5 main at-scale design philosophies. Optimize for the most common case. So that's something that most people do within infrastructure is, okay, what does most of my people care about, and they optimize for that. Prototype and iterate. Usually you want to get data as early as possible when you're designing something. So you build a prototype, you build like a hack, I have seen scenarios where engineers themselves like put together a CPU and a sled, build a rack in their basement, and they say, hey, this rack can do this application very well. Can we make 10,000 of these? So because they are able to collect that data. So they try to do prototyping and And 1 in a million is actually an everyday scenario. When you're working with this type of data and this type of scale, you should be afraid of 1 in a million problems. Like 1 in a billion, maybe you can ignore, up to like 3 months, but 1 in a million is an everyday problem. And the key 3 things that infrastructure usually looks for is performance, power, and reliability. So these you can define them as like 3 pillars. And the final point I want to leave behind is check every assumption, because you assume that CPUs are supposed to work, but when the assumption fails, your whole infrastructure can be at risk. How is performance aging tested and accounted for a new developmental advancement, especially in hardware design? So there are tools to do evaluation of a device within a life cycle. So what you would do is you would run high temperature testing, and when you expose a device to high temperature and also run your application workloads, you would be able to predict how the devices would perform at 3 years of use cases, 5 years of use case. So there's a term within the industry which is called HTOL. You can actually Google this term and you will get like a nice specification on how that would work. And that's the first set of tests. There's also some kind of a degradation testing that happens where people intentionally change the voltages and currents that the device is operating at. So let's say I manufacture a device. I will say, please operate this device at 1 millivolt and 100 milliamperes. I can easily change that configuration using like some register and try to push the device to its boundaries and see how it behaves. So usually when wear out happens, like when aging happens, your boundaries are not well respected. So you need to have more margin on your devices so that instead of 1 millivolt, if I run at maybe 1.5, it should still be okay. I have another question, which is with respect to the current geopolitical tension. Can India develop its own fabs and also homegrown chip designing companies? Like, are we too far behind to catch up to the current leaders? So this is a very good question. Actually, it's near and dear to me because I feel bad every time we see companies which are not Indian capable of developing new chips or fancy new technology. In my opinion, we have the talent, but we are not executing to our full potential. Like I feel like this should be some government sponsorship. We should be able to like develop our own fabs or chip design companies. It's a great asset to have. Right? Imagine a scenario where you want to do something that is very specific for Indian application. Right? As of now, we are dependent on foreign companies for doing that. Like we have to go to foreign companies and say, this is what we want to do. There's still research in DRDO. This, we try our best, but it's still not enough because the technology advances faster with foreign companies because, they have bigger investments. So I would say it comes down to investment. We can still catch up. I feel like, it's just about aligning the right incentives and giving people the motivation to say, this really matters to us. I hope we do it actually. That's personally would be awesome to see if we get more investment into this domain. Okay, I have another question. With transistor shrinking to a size under 5 nanometer and gates being shrunk proportionately, we are moving from being limited by electronics to being limited by quantum mechanics. Doesn't this suggest that software optimization is the way forward as hardware level optimization is only going to yield minimal gains? Yes, that's actually a very relevant question. So I don't know if people are aware, there's a conference which is called as ASPLOS. It's a well-known international conference. The keynote of that conference actually addresses this exact question. And it's about talking about compiler design for the quantum mechanic limitations, right? So you've done everything you can in hardware right now, which is, designing CPU, designing accelerators, and at some point, you will not be able to do future designs. And the onus for getting better performance comes down to compilers as well as our software architecture. And they have to understand that, maybe there will be like 40 or 50 hardware different companies, and they all have to agree to one standard and write code which can work on all of these devices at once. So that's a unification that we need to see within the industry moving forward. So there's actually one lecture from that conference, which is the ASPLOS. There's also a lecture from Hennessy and Patterson, who are considered as like the gods of computer architecture. And they talk about the importance of scaling in software. ASPLOS, ASPLOS. And you're absolutely right in saying that, right? We need unification of compilers. We need people to write code which is applicable for ASICs. Let me walk through the problem, right? Like everyone is now manufacturing their own ASICs and saying, this is how you write code for this special chip. And the problem with that is eventually you will see 100 chips and everyone telling you, I need to write code in 100 languages. That is simply not scalable when you want to make good progress. You want everyone to contribute to one project instead of everyone split across 100 projects. We need to make sure that there is one translation layer between hundreds of these companies manufacturing hundreds of chips, but we will be able to write code in one language which translates to all of these devices. And that's very important moving forward. I just want to say thank you. I know a lot has been going on in India, so please stay safe, everyone. Take care of your families. It's really painful to see some of the images actually. So I can take questions on infrastructure, semiconductors, engineering, as well as research careers and technology. What are your thoughts on Starlink and similar services replacing undersea cables? Yeah, I read this tweet from Elon Musk actually, and he was saying that within a couple of years we will have Starlink ready to beam internet to cities. I would say the reliability of that would still need to be proven. Undersea cables guarantee you connection today, right? There's a lot of infrastructure as well as a lot of money that has gone into ensuring that works. So replacing that is a big ask with Starlink. When you look for reliable network connectivity, what you want is buffers, what you want is a fail-safe mechanism. Because imagine if a cable goes down, you lose connection between Europe and US. And that's basically half of your infrastructure traffic. So until we see that, we will not be able to say Starlink is at the same level. But it's an excellent, I would say it's an interesting concept. Beaming internet, it takes away the need for wires. I'm also concerned with how much astronomical interference it will do. I have seen concerns from astronomers saying that it's creating problems with them trying to photograph planets. But overall, interesting idea. We probably have to wait 3 to 5 years, I would say, before we can talk about replacing undersea cables. It's a good goal for them, but reliability has to be proven for us to use that technology. I have a question which is about, I recently read about an initiative by Facebook called Glow. Can you throw more light on it? So yes, Glow is actually a very interesting software compiler that has been developed for the exact problem that we described. Right? So you have your ASIC devices, and ASIC devices would like to be agnostic, and you would like to program for your ASIC devices. So Glow is basically an initiative from Facebook to use a compiler, which based on however many ASICs you use, based on whatever code they want you to write for using that ASIC, you write one set of code, and the Glow compiler should be able to smart enough and translate it. So that it follows along the same lines as was discussed in the previous question, which is about software optimization. And I'm very excited. I think it's currently in production within Facebook as well, and you might have seen papers as well as the publications. Any advice for aspiring system architect? I just know the basics of Intel 8086 processor. What should I do? I would recommend following a professor called Onur Mutlu. He teaches a course at ETH Zurich, and he has a very good set of content as well as presentations for computer architecture. And yeah, so for me, I would say that's the go-to resource. Start thinking about systems actually. Every time someone says computer architecture, it's basically understanding what the interfaces are, right? So you need to know what your contract is for everyone, right? If you're designing a CPU, your contract is to give power performance. If you're designing a block within the CPU, you have to again start breaking down your contract and saying, okay, which signals am I responsible for, and why are these the signals I'm responsible for? And if you start breaking down, you start questioning the ownership that you have as well as the interface contract that you're negotiating. And that basically computer architecture is all about you are understanding trade-offs. If you know your interface, you know what trade-off you're making and what you're paying for and what you're losing. So any device that you see, if you see a mobile phone, right, break it down. If you break it down, you will see that there's memory controller, there's sensors, there's screen area, there's CPU, there's analog geometers and all of that stuff. So now you start looking at, okay, how much do I care about each of these things? And how much cost am I willing to pay? How much, how much power am I willing to consume? Can I run some of these in low power mode? Can I run some of these in high power mode? Right? So once you start understanding how to break things down, then you start questioning the decisions. And what if I do something else? You will actually end up with a different device. So that's why you will see a difference in performance between the Samsung phone, Apple phone, or like, some other model, because they made different decisions when it comes to the trade-offs that they wanted to go for. So that's how I would say, like, focus, break down things in systems, focus on interfaces, and you should be a good system architect. And another question is, how about ARM being the future of architecture, replacing x86, x84, considering NVIDIA's acquisition of ARM and a possible pull from open source? So this has actually been a very good discussion point within the infrastructure community itself, right? ARM, it has its advantages in that it can be significantly low power. So think of it this way, right? Every time you change your CPU, like if it's x86, you have Intel and AMD. But instead of x86, if you had ARM, your whole software stack changes because it is a different instruction set, which means you need to rewrite every code you have written until today to ensure that that stack works. And that is the challenge. So but it's an interesting proposition. And if there are benefits, people would definitely do it. So it's all about, again, like if I rewrite all of my code, what benefit do I get? Like, do I get a better performance long term? And if the answer to that question is yes, people would then go for ARM. NVIDIA as acquisition, I think there's still the process is still ongoing. So, but it's exciting, right? And when you have choices as a computer architect, you have like a lot more flavor to like what you can design. You can merge things. You can like say, how about I do this for this use case? How about I do this for the other use case? It's very interesting, like to have more options. Another question: things like the M1 chip, which has RAM modules and GPUs within the single chip. It's a concept that is like popularized by a few companies, I would say. In large scale infrastructure, I would still be like calling everything sort of an SoC because it's a lot of things which are put together. But in a consumer space, let's say if you're designing like a consumer electronic device, you would probably go for like architectures like that. I mean, especially Apple does a lot. I'm assuming it's Apple M1 and not ARM M1. So if it's Apple does a lot of things which are like very interesting, right? So they have a vertical stack. What that means is like they manage their own hardware, they manage their own software, so they have a lot of freedom in how they control and how quickly they want to integrate things. So because of that, they will see a lot more unification in how they do designs. Question: so can the RISC-ISA become mainstream? So there's actually a lot of backing with respect to RISC-ISA. Again, I want to reference the conference talk that I mentioned. That there's a lot more traction, like and a lot more companies are sponsoring RISC. But the goal there is to like unify again. You want something that is open source and not proprietary, and RISC-V gives you that flexibility to say, right, this is what I care about, and everyone can contribute towards it. And you make better progress and more people are involved. I would say it's still like 3 to 4 years away, to be honest. We need to see a lot more investment, a lot more engineering support for it. But it's good that it's getting to the mainstream. Like it's been talked about for a while, but it's really good that it's seeing mainstream. So it's an interesting domain, like similar to like NVIDIA's ARM. I would say it's interesting progress. But RISC-V being open source actually gives a lot more freedom. Question: does the efficiency of computer architecture of companies like Apple, Samsung depend on the cost investment done for developing it? Yes, of course. So with computer architecture, the key thing is identifying what works, and to get to that point, you will usually take significant number of iterations. So you usually end up trying a lot of different things before you get to this sweet spot, right? So you will say this cost, this power, this performance, and it gives me everything I want. But identifying that sweet spot is a 10 or 15 variable equation. It's very difficult to do it. Like it's sometimes even if you do everything right, things may not work well when you actually get the device back. So you'll do everything right. You'll do your evaluation. You will send the device to fabrication. When you get it back, you don't know like how electrically the materials are interacting with each other. So yes, I would say Apple and Samsung, people who have invested in this understand this a lot better than people who are starting out, for sure. But there's always disruption, right? So there's always a way to say, what if I change one fundamental assumption? What if I write a completely new instruction set and do something totally new, but it satisfies a very small set of users? You could always do that. And you will then be this disruptor who is kind of challenging the big companies, but at the same time, big companies don't care about you because you're like, hey, you're meeting the needs of one market, and then they don't care about that market. Like, so that's usually how people start up, right? You choose one domain which like larger companies are not interested in, and you become the best in that domain. So then you kind of build on top of that. So there's again a resource that I can cite. So there's actually a book called The Innovator's Dilemma, which talks about this very specific question that you mentioned, like big companies versus small companies, and why there is always room for a new idea. I have another question. Considering the recent silicon shortage caused by the massive surge in consumer electronic demand, do we have alternatives to look forward to in the near future, or are we tied to silicon? I'm pretty sure, everyone here has read about quantum computing. The problem with quantum computing is the operating temperatures that are required for us to consistently get the same performance as we get from a silicon. It's 3 orders of magnitude or 4 orders of magnitude better in terms of performance, but the cost that you need to spend to ensure you have the right temperature, the right environmental conditions. There's actually a special lab where they ran that quantum computing experiment to publish that paper, and you can't have that special lab be there in every data center. It's just too expensive. So I would say we are tied to silicon. Silicon shortage is also a supply chain issue, I would say, because of COVID, because of a lot of other factors, you will see silicon shortage. But there are so many smart material science engineers who are working on it, right? So they will come up with usually compounds of silicon. So they will find silicon, if silicon becomes short, they will find a compound which may require 10% silicon, but it can work with some other chemical, chemical properties. And you will find another material which goes with it. You'll create an alloy which still has the same electrical properties, and you would still do it. So that's usually the technique that has been used for shrinking the technologies until today. But yeah, I would say quantum computing next 20 years, if we can get the costs of operation down, we should be able to do it.
Seeing as there are no other questions, let's move on to the next part of the session, that is the vote of thanks. I'm Niharika PV from the Department of Electronics and Telecommunication, and I'm honored to present the vote of thanks for today's webinar. On behalf of BMSE IEEE, I would like to thank our speaker, Mr. Harish Dikshit, for sharing his valuable time and knowledge with us. Today's webinar helped us gain much more insight about the life cycle of a CPU within the infrastructure world while traversing both the hardware and the software realms. Thank you, sir. I would also like to thank the coordinators for making this event a reality. Last but not the least, I would like to thank everyone in the audience. Thank you for being so interactive and such great listeners. Hope every one of you had an informative and exciting session. Thank you.
Thank you so much.
Thank you.
Yes,